Here's an example with capacitors in series and in parallel. So we have an arrangement of capacitors and we have to find the total capacitance of the circuit and the charge on each capacitor as well as the potential difference across each capacitor. As usual, draw a diagram. So my diagram is going to be up in the corner so that we can look at it as we're doing the problem. First of all, to find the equivalent capacitance of the entire capacitor, it's going to be useful to identify which ones are in series and which ones are in parallel. Well, here it seems pretty obvious that capacitor 2 and capacitor 3, the 2 microfarad and 3 microfarad, are in series. So we'll start with that. Capacitors in series add like resistors in parallel. So if two capacitors are in series, I add their inverses and take the inverse of that. If I'm calculating in microfarads, that's 1 over 2 microfarads plus 1 over 3 microfarads, and then I take the inverse of that. That's 3/6 plus 2/6, and then we take the inverse. The equivalent capacitance of capacitors 2 and 3 is 6/5 of a microfarad or 1.2 microfarad. Now the equivalent capacitance of capacitors 2 and 3 and capacitor 1 are in parallel with each other, and capacitors in parallel add like resistors in series. So 1 microfarad plus 6/5 of a microfarad is 11/5 microfarad or 2.2 microfarads. Then the equivalent of the three first capacitors and capacitor 4 and capacitor 5 are in series. So 1 over 4 microfarad plus 5/11 microfarad plus 1 over 5 microfarad, and taking the inverse of that gives 220 over 199 microfarad or 1.11 microfarad. That was part A. Now let's figure out how much charge there is on each of these capacitors and what's the potential difference across all of these capacitors. First of all, we can find the total charge on the total capacitor arrangement. All we need to do is multiply the capacitance by the total voltage. 1.11 microfarads multiplied by 6 volts is 6.66 microcoulombs. The 4 microfarad capacitor, the equivalent capacitance of capacitors 1, 2, and 3, and the 5 microfarad capacitor are all in series. This means that they all carry the same amount of charge. So the potential difference across capacitor 5 is 6.66 microcoulombs divided by 5 macrofarads, and that's 1.33 volts. The potential difference across capacitor 4 is 6.66 microcoulombs divided by 4 microfarads, and that is 1.66 volts. The voltage across the equivalent capacitance of the parallel arrangement is 6.66 microcoulombs over 2.2 microfarads, and that is 3.03 volts. And you should always take this opportunity to check your work. The sum of the voltages across my capacitors is equal to 6 volts. Awesome! And with the voltage across the parallel capacitor arrangement, we can figure out how much charge is on capacitor 1. So 1 microfarads multiplied by 3.03 volts is 3.03 microcoulombs. And now we can find out how much charge is on the 2 microfarad and 3 microfarad capacitor. So 1.2 microfarads times 3.03 volts is 3.64 microcoulombs. Here's another opportunity to check our work. And if I add up the two charges that I found, I get 6.67 microfarads, which is equal to the charge on capacitor C4 and is equal to the charge on capacitor C5. Awesome! Potential difference across capacitor 1 will just be 3.03 volts. The charge on capacitor 2 is equal to the charge on capacitor 3 because capacitors 2 and 3 are in series. That makes the potential difference across capacitor 2 3.64 microcoulombs divided by 2 microfarads, which gives 1.82 volts. The potential difference across capacitor 3 is 3.64 microcoulombs divided by 3 microfarads, and that is 1.21 volts. And here's another good opportunity to check. 1.82 volts plus 1.21 volts are 3.03 volts. Awesome! And here is what the layout of my pages looks like. Spread the joy of physics!